Okay, our next talk is going to be given by Francis and Robert, and they're going to talk to us about OpenTelemetry and Shopify.
Okay, so we're talking about OpenTelemetry and Shopify. Who are we? I'm senior staff on observability. I've been at Shopify for 11 years, and I'm the founding implementer of OpenTelemetry Ruby. My charming assistant, Robert, is staff engineer on observability. He's been at Shopify for 6 years. And he's a maintainer and the number 2 contributor to OpenTelemetry Ruby. What is OpenTelemetry? Well, firstly, it's a bit of a word salad. There's a lot of terminology here, especially as you dive deep into metrics, for example. For OpenTelemetry itself, though, we mean 3 main things. Firstly, there's the specification itself. Then there's the implementation, both the collector and the libraries for various languages. And finally, there's the community. Let's start with the specification. So the spec is motivated by a handful of important concepts. A key organizing principle is the 3 pillars of observability. The spec addresses logging, metrics, and tracing mostly separately, with some more experimental work ongoing for profiling. There's an explicit separation between the API and the SDK for each language to allow alternative SDK implementations. And the project was created with the express purpose of unifying open census and open tracing, where open census addressed both metrics and tracing. And a lot of the early focus aimed to ensure that there were bridges or shims that could be built for the existing implementations of both of those earlier efforts. So another early decision was that we needed to build auto-instrumentation, particularly for data access and communication libraries. And the hope was that as the project gained traction, those libraries would adopt OpenTelemetry native instrumentation. Tracing was the first signal that we tackled. It requires passing around correlation IDs and some other state for sampling and to stitch the trace together. This is managed in process by a language-specific mechanism called context. So in Go, for example, we leverage the existing explicit context.context idiom. In Ruby, we mostly manage it implicitly with thread local variables. Context also has to be propagated between processes, for example, in HTTP requests. Roughly at the same time, OpenTelemetry was being developed, and with roughly the same people, W3C developed its trace parent RFC, and that was adopted as the default for context propagation between processes in OpenTelemetry. And finally, we need to export telemetry somehow, and a new protocol was developed using protobuf and gRPC called OTLP. So as an alternative, the same data can be exported as protobuf or JSON-encoded OTLP over HTTP. Next slide. So as I mentioned, there's an explicit separation between the API and the SDK, both in the spec and especially for packaging. The API contains a no-op implementation that allows instrumentation to work without a SDK installed, and alternative SDKs can be plugged in as the global implementation. The API exposes metrics and tracing. Logging is considered a legacy signal. So it's assumed that there's so many logging APIs that exist that it really isn't worth trying to supplant them with something new. So cue the XKCD standard strip. So only a SDK is spec'd for logging. The SDK focuses on operator concerns like configuration, resource detection, say information about the execution environment, telemetry, export, and sampling. And on the other hand, the API focuses on instrumentation. So standardized telemetry mechanisms are helpful, but without some policy, the data ends up ad hoc and poorly organized, and it's really hard to do anything useful with that. OpenTelemetry introduced semantic conventions for many commonly used instrumentation scenarios. And the semantic conventions enumerate attribute names and types, what they mean, which ones are required, which ones are optional for different types of span, for resources, for some common events. Having these conventions allows us to build more powerful tooling, such as analytics UIs and alerting, and write useful documentation that describes best practices. So moving on to data models in the spec, the tracing API is largely derived from OpenCensus, which describes a synchronous hierarchy of spans. Asynchronous relationships are modeled with references to spans in the same or a different trace. Open tracing compatibility is provided by semantic conventions. Attributes are everywhere. So resources describe the process environment, so things that don't usually change, like the process ID, the container ID, the cluster ID. Instrumentation libraries can contain attributes, but they're not used much. Those attributes would be mostly static, like I represent a MySQL database. Spans have static names, but mostly dynamic attributes, so things like endpoint or request parameters. Spans have start and end timestamps, and they're related by trace ID, span ID, and parent span ID. Events are owned by a span, and they have a single timestamp. They can have static or dynamic names. So depending on the use case, and they generally contain dynamic attributes. Attribute names are static strings, and there's a small set of types supported. So integers, floats, booleans, string, and homogeneous arrays of each of those simple types. Next slide. So the metrics API has a high-level event model and a low-level idealized Prometheus time series model. And this diagram shows the transformation from an instrument that's recording events to the exported time series data stream. A logging data model is similar to traces, just with more legacy stuff. The last major bit of the spec is a protocol to export telemetry. That's called OTLP for OpenTelemetry Line Protocol. The default encoding is protobuf, and the protobuf can also be encoded as JSON, which is useful for browser environments, for example. gRPC streaming is a default protocol, but we can also simply post encoded batches over HTTP. The protocol is mostly strongly typed, which aligns with the API. The prominent exceptions are maps and dynamically typed heterogeneous arrays, which the API doesn't support. There's a really straightforward mapping to the data model with nesting and grouping for efficiency. So for tracing, we have events nested under spans, which are grouped by their instrumentation library, and then a resource is at the top level of the batch. We have implementations of the API and SDK in all the major languages, probably including several that I've forgotten. I've said this before, the API and SDK are shipped as separate packages, which allows substitution of different SDK implementations. There's an emphasis on legacy compatibility in the spec to provide a migration path. So exporters are required for older telemetry formats like Jaeger and Zipkin, along with legacy propagation formats like Ubers and the B3 propagation header from Zipkin. The new telemetry format is OTLP, and the default propagator is W3C trace parent. Auto instrumentation is essentially required because most existing data access and comms libraries are not designed with telemetry in mind. The SDK needs to support configuration of itself and also auto instrumentation. Vendors are encouraged to package supported or recommended instrumentation with a pre-configured SDK, and so AWS is a prominent example of this, and we do the same here. The community for OpenTelemetry is overrepresented by observability and cloud vendors. For a long time, Shopify was pretty much the only significant end user in the community, and Robert will talk later about the impact of that.
So I'll go over a brief history of OpenTelemetry and Shopify. Prior to OpenTelemetry, we used custom libraries built internally. Our supported languages were Ruby and Go. The libraries took design inspiration and were compatible with open tracing. That library came batteries included, so it had the auto instrumentation and everything needed to create and export spans. There were some challenges with that I'll kind of touch on later. During this time, we had a very custom collection pipeline with exporters to both commercial and open source backends. With plans to move to open source solutions, we were set to take over maintenance of Open Census Ruby. OpenTelemetry was announced around that time, so we quickly pivoted to implementing the OpenTelemetry API SDK and contributed instrumentation for many of the Ruby libraries. As we were implementing OpenTelemetry Ruby, we also became very early adopters of the Otel collector. Our first Otel OTLP exporter was actually implemented in our custom Ruby library and then later ported to OpenTelemetry. After Tracing 1.0 was released, we started building an early prototype of the metrics API and SDK, but ran into some issues, which again, I'll touch on later. Having now spent a few years with OpenTelemetry, we do have some things to say, and I'd like to start with some of the good stuff. The community of like actual maintainers and contributors, pretty great. Like for Ruby, we've had a lot of good fortune with like GitHub and New Relic, and more specifically, the people that came out of there. The semantic conventions have been really useful to us internally, as we have a single documented place to point people to for naming conventions. And while we don't perfectly adhere to it, it is a nice goalpost to move towards, and we can use it across telemetry signals. We're using it in logging with the latest work we've been doing there. Since the release of OpenTelemetry, we've seen an uptick in like both interest and just general familiarity around tracing. That's been like kind of a long-term challenge, as tracing can be a little bit overloaded. We see people refer to it as profiling and tracing, et cetera, et cetera. It's easier just to engage with users when we have a common language to use. The reference specification, so like the spec for the API and SDK, it helps a lot for disambiguating behavior. It's like, what is it supposed to do? Well, what does the spec say? Having the API separate from the SDK means minimal dependencies added when embedding first-party instrumentation. So I was saying before with Shopify tracing, our first kind of pass at this, everything was included. So Cusco had a dependency on Google Protobuf, and then there was issues upgrading it, and it just turned into an entire mess. So the API almost predominantly depends on just Ruby. So adding it as a dependency doesn't come with all the baggage that the all-in-one had. We have common collection infrastructure now and commoditized instrumentation. So it means it's really easy to evaluate different vendors and open source solutions. We don't need to deploy a different collector every time, just update the exporter config. There have been some challenges with the OpenTelemetry project. As Francis said earlier, the project has a lot of vendors weighing in on the direction, which is not like inherently bad because you get a lot of support for it, but end user involvement has been minimal in comparison. And a customer feature request is not quite the same as proper end user advocacy. And so there's this example that I like to bring up, but I'm gonna try to keep it a little ambiguous. So a vendor comes in and says, hey, we need to make this spec level change to instrumentation. Our customers are having this issue, and you know what? We can't change their code because they're the customers. We can't add environment variables. So what we should do is add a shit ton of overhead to all the instrumentation because I don't want to engage with our customers. They didn't say it like that, but that was the general tone of it. The real problem with that is I had to spend literal months of going to multiple meetings weekly, so months of going to weekly meetings just to say, hey, you know what? It's not acceptable to add this overhead to all instrumentation just so you, don't have to talk to your customer? It's crazy, it's crazy. So we obviously recognize the importance of performant instrumentation, so we put a lot of effort into try to advocating for it, but again, it does feel like an uphill battle. Following a similar pattern during the design phase, a lot of emphasis was placed on Go and the collector, but the same affordances weren't given to language implementations. And really close to home, for example, the encoding performance of OTLP and Ruby could be a lot better. Let's talk a little bit about specification challenges. Our efforts towards building the initial metrics in API SDK was largely hindered just by the amount of churn that was happening to an already very verbose specification. I like to joke that like whoever wrote it had a newly acquired thesaurus. Like, it's awful. By the time it reached stability, our focus had shifted away from implementing the metrics API and SDK. It wasn't a priority for us at that point. But we have had some challenges with the tracing specification as well, even if it's a lot more concise in comparison. The big one for us is it doesn't allow for muting spans in process after they've been finished. Or at least it doesn't allow for it to be done efficiently. So this is a big challenge for, it's a big challenge for us, but it is a challenge for the community as well. So this is where we talk about end user advocacy. Not everyone deploys their own collector. We do, so we have the affordances that come with that. But what if you're an app that doesn't deploy their own collector and you have a strict requirement for redacting PII in process? You don't have a way of doing that efficiently. So now you're paying a lot of performance penalties for that. Common asks from the community include the desire for block-based setting of attributes. So you have your block, do, end, and anything in the middle you want to append an attribute to. There's not an efficient way to do that. Baggage is propagated across services. So I want to write this attribute to all spans downstream. So I write in the baggage. There's not an efficient way to do that. A really concrete use case for us is we like to capture GC stats on the spans. So the way we do it is we actually create a temporary attributes hash. We write the start, then at the finish, we duplicate that hash, compute the delta, and we have to duplicate the hash because it's frozen, and it's frozen because the spec says it needs to be frozen. So there's this like stupid circular waste of efficiency just because we're trying to remain spec compliant. Challenges at our scale. So the sampling specification makes it impossible to sample internal spans without breaking the trace. We had to monkey patch the SDK we were maintaining. So what that means is you have a trace and then you can have consumer, server, producer, client, and internal spans. And internal spans, basically, what that means is it's like not receiving communication or making communication to some outside service. Why do we sample internal spans? It's volume control. Right? We sample internal spans while preserving the structure of the trace, and we call it verbosity sampling. So if anyone's ever heard the verbosity sampler, not all of our traces are verbose, but all traces preserve the distributed graph, and we do our best to keep as much as the high-value data. When I say like just preserving the distributed graph, it's like when you connect the dots, there's not missing pieces across like the service map. This results in just no broken traces, and we can significantly reduce our overall volume. But it did require us kind of monkey patching code we maintain just to stay spec compliant. The spec also requires that samplers return a sampling decision plus an attribute hash rather than just updating the existing hash. And the sampler is evaluated every time you create a new span. So if you've seen a trace with 1,000 spans, there's been the sampler call and 1,000 hashes allocated. So we had a patch and we did a bunch of work to minimize allocations and compute. We have to like cache the sampling decision up front, and we have a bunch of rules that get evaluated, and we put a lot of work into try to minimizing the overhead. And a lot of that overhead could be avoided with a more conscious specification around span creation. People on the tracing team have heard me complain about trace parent and context propagation woes. So what that is trace parent is this open standard for a header key. This is how you transfer it across service boundaries. So you have Shopify core, you have external API clients. Some awesome app decides that they're gonna recycle the same trace parent for 2 days on every single request. Your trace is now millions, hundreds of millions of spans, and it's completely broken. So how do you solve it? One way, at ingress, you can strip trace parent, cool. But what if hypothetically you have a vendor who also intercepts your trace parent and then injects their own new span and emits it to their backend, which you don't use. So now you're stuck with broken traces by default and you have no recourse unless you write trace propagators for every single language implementation. So we're talking Rust, Go, Ruby, Java, JavaScript, Python, and something else. And that doesn't include like hypothetically Envoy. Are you gonna recompile it from source and deploy it so you can fix this? No, the spec could have done the hard thing of looking at these problems and actually dealing with them and maybe made trace parent configurable via nvar so that everyone that was spec compliant, you could just have an nvar instead of doing all the bullshit I just said. We're going to talk a little bit about the future of OpenTelemetry at Shopify. So one of the things that's come up a few times now is forking the audio instrumentation libraries. They can be difficult to maintain, so library authors don't often create formal instrumentation hooks. So we're forced to monkey patch internal APIs that can change between minor and patch releases. And because we want to be a healthy community, we have to add all the complexity of saying, if it's this version, use this patch. If it's this version, use this patch, and so on and so forth. You kind of get it. It becomes a bit of a dependency hell. But at Shopify, we have a small set of accepted libraries which are kept relatively up to date. We've all seen the Dependabot PRs, right? So we don't need the same level of backwards compatibility with the open source community. Our internal domain experts also would be able to just kind of experiment more freely. Because right now, we've actually run into a few times where someone's like, hey, can I add this attribute? It's like, well, we're using the instrumentation of the open source. It's not spec, so technically you can't. And then we're kind of left like, what do we do? Do we not add it because of some arbitrary like rule, or do we fork it? And you're kind of left in a spot where it's like nobody feels empowered to make changes to improve the system. So being able to deviate from the spec freely means we can make decisions that are best for Shopify and don't have to refrain from things like that. But it would mean that we'd be pulling away from the open source community, which we shouldn't take lightly because we could miss out on getting wins from the community and also just the good of giving back to it. So in the same vein of forking the third-party instrumentation, there is an opportunity for more first-party instrumentation. It has been difficult to get library authors to adopt OpenTelemetry. What's the incentive for them? Like, they don't know if OpenTelemetry is just a phase. Does it have lasting power? What's the merit of time investment? Not all library authors are telemetry experts. Like, are they holding it wrong? Are they measuring it right? Semantic conventions have had a long time to stable. Semantic conventions have had a long tail to stabilize. So would the expectation be if some first-party instrumentation was created, would they just keep updating as it gets, and then people who are consuming it, their attributes are changing? It's kind of tricky, but as we see a bit of a pattern of us internally moving to more in-house data access libraries, we do have a pretty good opportunity to embed Otel instrumentation directly into the libraries and less reliance on monkey patching, which is related to a good handoff for Francis here.
So first-party instrumentation is particularly relevant as we move more I/O functionality into Rust, which we're seeing initially for a few data access libraries. For a dynamically typed language like Ruby, the spec imposes a bit of a performance ceiling. So to help raise the ceiling, I've been implementing the OpenTelemetry Ruby tracing API in Rust. The key principles guiding this are don't expose SDK functionality to application code. So we don't have span processors, exporters, span data, or resources available to Ruby code. And by pushing telemetry eagerly to native memory, we can manage the lifecycle of data explicitly, which eases the burden on Ruby's GC. Exporting and particularly encoding without holding the global interpreter lock significantly reduces the negative impact on the application's tail latency. Since we control the implementation, we can implement custom functionality like VM and GC metrics directly instead of monkey patching the SDK or resorting to mutating span processes. Performance wasn't a goal of this work. We aimed for no worse than Otel Ruby overhead. We were mostly focused on the later aspects of serializing and exporting data. But the naive implementation was actually worse. So we invested some effort to make it better, and then we somewhat overshot because profiling is addictive. Let's look a little further into the future. As I mentioned at the start of this talk, OpenTelemetry embraces pillars in its data models, its APIs, its export pipelines. On one hand, this leads to a lot of duplication, such as requiring independent exporters for each signal, so potentially 3 background threads if we're implementing logs, metrics, and traces. On the other hand, it increases the API surface area that needs to be understood to use the signals effectively, and it misses an opportunity to simplify and unify telemetry. At a high level, telemetry signals like metrics, traces, and logs are all simply events, like X happened at time T with some context. The differences are largely a matter of how much context is implicitly recorded. So traces like logs with an implicit duration and causation and correlation IDs. How they're consumed, so aggregate time series versus discrete events, and encoding and export efficiency. So as a first step, we'd like to lean into the similarities between logging structured events and recording traces. In particular, at Shopify, both these signals have similar constraints. So they support similar attribute types. They have similar data models. They share their data store, ClickHouse. They share their data access API and the UX. They differ in their export models at the moment, but that's a historical accident rather than kind of design essence. Given the success with performance improvements in Observe Instrument, we want to extract the structured logging API from core, re-implement it in Rust, and provide a simpler API at a lower level than OpenTelemetry, with context largely implicit and event-focused. So, for example, in core, we have observe with attributes, which supplies attributes that are just added to all events in the scope. We'd like to do the same thing to apply attributes to all spans within a scope. Spans are simply a pair of start and end events. So they're remarkably like structured events. They have this pair. Usually we only emit one. There are circumstances where it might actually be interesting to emit two. Batching, encoding, and export of a common event stream improves efficiency and removes duplication. Building an OpenTelemetry tracing API shim above this low-level API will allow us to leverage existing instrumentation in our applications and libraries and auto-instrumentation for third-party gems. And finally, Rust and Ruby interop is increasingly important at Shopify, especially for data access and communication libraries. So we need to provide a mechanism to share or transfer telemetry context between Ruby and Rust in both directions, and allow Rust developers to instrument their code in an idiomatic way. The Tokyo tracing crate has overwhelming mindshare for instrumentation in Rust, so we want to make sure that we can leverage that. So now you know a bit about who Rob and I are, what OpenTelemetry is about, the history of OpenTelemetry at Shopify, some of the highlights and lowlights of OpenTelemetry based on our extensive experience implementing and deploying it at scale. And some future directions for OpenTelemetry at Shopify. So thanks for listening.
Thanks.